Hello, my name is Jamie Wynn. I'll be presenting stage 1 for our team's final project for DS Duel 1. I'll be aiming to describe our project and answer these 3 questions. What kind of question is our project aiming to ask? What's the dataset that we analyzed? And what kind of benefits or patterns can we expect to glean from this dataset? So, the topic that this project analyzes is player injury in soccer. We're aiming to discover what kind of factors are associated with causing player injuries in soccer. For example, do defenders get injured more often than strikers, midfielders? Well, to do this, we utilized this dataset that was available online on the GitHub repo. This dataset focuses on factors potentially related for predicting injury risks for soccer players. It contains 1,903 rows, which all represent an instance of a player during the season. Each player has associated with them various attributes, both numerical and categorical variables. Some of the more noteworthy attributes, for example, associated with each player are the number of games played in the current season, how many minutes total they've played, the number of shots taken, and most importantly, of course, the number of injuries they had received. In addition, associated with each player are categorical attributes as well, such as, well, the player's position. So, coming into this dataset then, we had hypothesized a couple of different patterns. What do we expect to see? Firstly, we tried predicting what factors were likely to be the main predictors of injury. Are there specific characteristics, like how old is a player, what's their position, how much time do they get on the field? All of these could be factors in injury rate. We also tried finding out the correlations of some match performance metrics that were unexpectedly heavily correlated with each other. And of course, we also took into consideration any outliers, like in any sport, or like in this dataset. We could see individual outliers amongst these 1,903 players analyzed. Outliers like my goat, Mbappe.
My name is Tumidi Mohammed, and I'll be going through the data collection portion of our project. I'll be answering how do we find our data, how do we download it, did we scrape it from the internet, also how do we go about cleaning it, or was it necessary for our project. I'll start off by saying we grabbed our data from a GitHub repository, which had lots of data of soccer-related injuries. We were then able to download it in a CSV file and load it into our pandas. The way we went about cleaning up our data was dropping all null values, since those wouldn't be helpful. We also deleted all duplicate rows. After cleaning that bit of data, we then deleted the old position column and were able to kind of upgrade it so that we would know which player by their position. You can see that we then updated it that way, and we dropped the entire position column altogether. We then created a new column called currently injured, and this would be a Boolean column, so they're either injured or they're not injured, and that would be very helpful for answering our question later on. This is the current state of our data. On the right, you can see the newly created column called currently injured players. So you can see false or true. And on the far right, it's kind of cut off, but you can see the position of players, which we did not have before, and that was able to help us draw more insights from our data.
Okay, so after we gathered the data, we went to explore the data. So one of the things we knew or intuitively thought was some of the things that could affect player injury is player age or like their physical attribute that's going to affect injury rate. So what we did when we went into a descriptive analysis was we tried to figure out the age range of the data set first, as we first thought age was a factor in, or age affects injury rate. So, according to the descriptive analysis, we see that age, the average age is about 26.9, 27 years old, and the lower quartile is about 23.7, and the upper quartile is about 29.9. So immediately we saw that the data set was leaning towards some of the younger side. So we had an idea of not trying to analyze this data set based off of age and try to go towards more of a physical attributes side. So we looked at more of the physical attributes. So the physical attributes, we can see that there's a total of 1,895 players, as 1,895 starts. So, and each player has a recorded statistics, and many of the main statistics that we looked at was shots, goals, assists, and tackles, as these are the main attributes in football. So, we decided to go towards a more physical attribute route rather than age because the data set was leaning more towards the younger range of ages. So we tried to look for some observations first. So first, we tried to correlate tackles with injuries, as tackles is a very physical aspect of football, as a lot of players could get hurt when tackling each other. So we made a correlation matrix, and as you can see in the correlation matrix, there's almost very little to no correlation at all between injuries and tackles. So we thought that was interesting because we thought there would be at least some type of correlation between those two types of attributes because it is um, because it is the tackles are usually seen as the most physical part of soccer. Okay, so then we can move on to some data exploration. So we did try to look at age a little bit more in depth. So we tried to see if there was any type of pattern or trend between age and injuries. But as you can see in this graph, there's a variety. There's a very big range. Like injuries that happen are usually typically happen between ages of 20 to around mid 30s. So it was a very big range. So we decided it is best if we focused on physical conditioning of a player to see which statistics injure the player the most, rather than looking at age. So, some hypotheses and predictions. So now that we moved away from ages, we tried to look at the positions the players play at. So as you can tell, the most injuries that happen to a player occurs at the defensive position. Um, it's a roughly about 5,800 on this graph, and then the second most is block thing, but it's strikers, um, players that take shots more. Um, so immediately we came up with a hypothesis based off of that the statistics that affect players the most or causes injuries the most is defensive stats because defenders are hurt the most. So we believe that defensive stats are the ones that's causing most injuries to players. So fixes to the data set. So I've already stated that we decided to not focus on the age group of um, the data set because there's no range between the ages. It was just between 23.7 to 29 something based on that quartile. So there was not enough data to cover 18 through 24 or anywhere older than 35. So we decided that we're not gonna focus on age as a factor in this experiment.
Model our data using the machine learning models. So the primary model we decided to use was the logistic regression model because it's good for trying to predict the probability that an outcome, like a Boolean outcome, injured or not, occurs based on multiple independent variables. Because we are trying to predict the number of injuries that a player could have given different game statistics in our data set. So for the training split, we decided to split it into the regular standard split of 80% training to 20% test data. And for the inputs, for the columns, we chose all the columns that have float types as their statistics. So the features do represent what we want to answer because each of the players' numerical statistics has some influence on the number of injuries that they could get over the course of their career. So as you saw in the correlation charts before, some statistics do have more correlation than others, but all of them do influence in some way. So we need to include all those float type columns. So we did scale our data, and then we fit the data on the model. So for accuracy measuring and cross-validation, we measure the accuracy of our model by first getting a prediction, as you see in the right, getting a prediction for the input testing values, and then producing an accuracy score on that model, and then comparing our output for the testing values to the prediction that we had. So, and then for the cross-validation scores, we called that method cross-validation score on our model and our training data with 5 splits, and then we trained the model on those folds, and then tested it on those folds. So hopefully this should reduce the impact that random variations should have in our data, because we're testing it on 5 random different folds. So we found that the accuracy was 58.27%, and then the mean of the cross-validation accuracy was 49.57%, which, as we'll see here now, we can compare that to these models. So we performed this accuracy testing and cross-validation on another 4 different models, KNN models with different K values and decision tree models with different depth values. So we did the same steps as we did earlier for the primary model, the logistic regression, and we got some scores, and then we compared these scores to our primary model scores. So we found that actually, after comparing the models, that our logistic regression model performed better than all of the models in terms of accuracy score, but only did worse than the decision tree model of max depth equals 4 for the cross-validation scores. So, and this is a comparison on the right here of all the different models and how they perform. So the decision tree of max depth equals 4 was best overall by far. So because our model doesn't necessarily do the best in all categories, we have to improve it somehow. So to improve our model, we decided to use the grid search method. So we defined a hyperparameter grid for logistic regression. And basically what's going on here is we're going to do the logistic regression, but given many different types of inputs. So logistic regression has types of inputs like random state, we has number of folds and stuff. So we want to input as many different types of inputs, right, that could occur, and then we're going to assess the model on all those different types of possible inputs, a larger array of inputs, and then see which input will produce the best result. We take that best result, as you see, the best model equals grid search dot best estimator. That will get us the best model and the best prediction and the best accuracy score. So after we do all that, we see that our cross-validation score improved by a pretty good amount, 0.0901, and an accuracy score by 0.1023. And after doing all this, we thought about it and we thought, okay, an alternative approach to getting a prediction for our data, maybe a better model that we could use would be the Poisson model. And since Poisson distributions, by how they work, model the amount of occurrences or hits that occur within a given time frame, it could be better for predicting the number of injuries a player could get in a certain time frame, like the amount of games they played, because each game is a certain amount of time, based on the statistics that they get during their games.
Okay, so after we trained our logistic model, our machine learning model, we decided to do some improvements to it to see which stats actually affects injuries. So what we did is we used feature engineering to improve the logistic model. So we first made a data frame by dropping some of the categories we didn't need. Then we did a for loop where we iterated through the features and added them one by one to see the accuracy differences, decreases, or increases to see which features help the model predict better. So first we hot encoded the data. We hot encoded the data frame to help improve the accuracy. Then after that, we concatenated the new feature that we added each time of the iteration into the data frame. Then we just scaled the data Then we trained the model using logistic regression. Then we predicted the model. Then we printed out what feature was just added and what the accuracy score was when we added that feature. So we discovered some new things, as we can tell. Um, After we added aerials 1, so the jumping and heading the ball, we see that the accuracy jumped by 12%, which shows that aerials is a very big attribute into how aerials is the attribute to how it's affecting injuries. And as you can see from tackle groups increases that accuracy 59%. So we can see that tackles and aerials, these two features, help improve the accuracy of this model, which suggests that these two features could be potential statistics that affect the injury rate. Um, so after all of our observations, data analysis, data manipulation, machine learning that we've done, we came to the conclusion that our hypothesis was supported, and our hypothesis initially was that defensive stats are the ones that affect injury rates the most. And we saw from the models that tackles and aerials showed jumps in accuracy when we did feature engineering. When we added tackles and aerials, we saw prizes in accuracies the most out of any of the stats. And tackles and aerials are one of the most defensive stats, as tackles where people tackle the ball, and aerials are trying to win aerial battles and heading. So these two stats are defensive stats. So our hypothesis was concluded, and to answer a question from the introduction, that which statistics affect player injury the most, we conclude that tackles and aerials affect them